Now we want to go through and talk about an inverse of a matrix, and that's going to be the key to helping us solve a system of equations. So if we think of real numbers, we do have an identity property. So if you take any real number, times it by 1, you're always going to get the value a back. Same thing, if you switch that order, doesn't matter, you're going to get the value a back. And it doesn't matter what you have. For matrices, we want to come up with the same type of process or same type of matrix. For matrices, we want to make a similar extension. So is there a matrix I can multiply a by to always get a back? And it doesn't matter which side we do that multiplication on. So if there's a multiplicative identity matrix, which we're going to call I for identity, such that if you take A and multiply it by this identity on the right, such that if you take A, multiply it by the identity on the right-hand side, you get A back. Or if you multiply by the identity on the left, you're still going to get A in return. Regardless of what your matrix A is, that's going to be our identity matrix. And the only way this can possibly happen if you do left multiplication and right multiplication and get the same thing in return is if you have a square matrix. So they have to be square and they have to be the same order. So the specific identity matrix is going to be the same for every single type of size and order we have. The n by n identity matrix is denoted by IN. 1 is that multiplicative identity. So here we've got a whole bunch of 1s on that main diagonal and 0s everywhere else around it. This is our identity matrix. So for 2 by 2s, you have a matrix, 2 rows, 2 columns, 1s on the diagonal and 0s on the off. For the identity matrix for 3 variables or a 3 by 3 matrix, 1s along the main diagonals, 0s on the outside. So let's just pick a random matrix. We're going to show when I multiply this by I2 on either side, I'm going to end up with A. So first, let's look at multiplying by the identity on the left. So I want to take my identity matrix and times it by my matrix. So we have a process again we have to follow. We're going to kind of highlight these. If I want the first row, first column, I'm going to deal with the first row, first column, and that's going to give me 1 times 4 plus 0 times 7. If I want to get the element in the second row, second column, so this row, this column gave me this piece. If I want to move on and to get the element in my multiplication of the first row, second column, I'm going to go ahead and multiply these two together. So we'll get 1 times 2 and 0 times 5. So that results from multiplying this specific row and column. Now if I move on and I want the 2, 1 position, I do second row, first column. So you get 0 times 4, 1 times negative 7. And then finally, to get that 2, 2 position, we do the second row, second column. So we get 0 times 2, 1 times negative 5. And indeed, if you do this addition and multiplication together, you end up with exactly the same matrix you started with. If we multiply by the identity on the right side, still going to result in a 2 by 2, but I'm going to take A and multiply it by I. Same process. I'm going to take the first row, first column, and that's going to give me the element in the first row, first column. So you get 4 times 1, 2 times 0. If I take the first row, second column, it will give me the answer here. So we get 4 times 0 plus 2 times 1. Then if we move on to the second row, first column, I'm going to get the piece here. So we get negative 7 times 1, 5 times 0. And then finally, second row, second column gives us the position, or gives us the element in the second row, second column. So that'll be negative 7 times 0, 5 times 1. And again, we end up with So let's start with an example. Let's show if we take this matrix A, which is these elements, and we multiply by the identity on the left or right, I'm still going to end up with exactly this matrix. So let's start by the identity on the left. So I've got my identity matrix times the matrix that I'm given. First thing I want to do, if I want that first position, and I take my first row, first column, it's going to give me the element in my first row, first column. So you'll get 1 times 4, 0 times 7 when you multiply those like components. Okay. Now, if I multiply the first row, second column, it's going to give me the element in the first row, second column. So you'll get 1 times 2, 0 times 5. If we move on and do the second row times the first column, that'll give me the element in the second row, first column. So you'll get 0 times 4 plus 1 times negative 7. And then finally, if we do the second row, second column, we're going to end up with the element here. And this should be a positive 5. So we get 0 times 2 plus 1 times 5 for this last piece. And so indeed, this does give us exactly the same matrix back, 4, 2, negative 7, 5. So we get the same thing, and that is A itself. If you multiply by A on the left-hand side and the identity on the right-hand side, we're going to repeat the same thing. So first row, first column gives me that first piece. So we get 4 times 1, 2 times 0. First row, second column gives me the position in the first row, second column. So we'll get 4 times 0, 2 times 1. Second row, first column will be the position here. Multiplying the like pieces gives us negative 7 times 1, 0 times 5. And then finally, second row, second column gives us this last piece, which is negative 7 times 0, 5 times 1. So if we go through this again, we end up with exactly the same thing. So this identity does indeed give us the same matrix back. Now, likewise with real numbers, every non-zero real number has something called a multiplicative inverse. So if you take A and multiply it by its inverse 1 over A, you end back with that identity value. So we have a similar concept for matrices. Can I multiply a matrix by something to give me that identity back? So if A is an n by n matrix, then its multiplicative inverse, which is going to be written as A to the negative 1, kind of like when we do function inverses, must satisfy both of the following equations. So if you take A and times it by its inverse on the right, you end up with the identity. And if you take A and multiply it by the inverse on the left, you end up with the identity again. So only square matrices are going to have inverses. So let's try to figure out So we'll come up with a process of how to actually find the inverse itself, but let's just start and see if two matrices are inverses of each other. And we're going to work with these two matrices pretty much for the rest of this section. So if I want to see if they're inverses, I've got to actually multiply them out. So we're going to get a 2 by 2 matrix in return, because this is a 2 by 2, multiply it by a 2 by 2. So if I take my first row, first column, and multiply those, we'll get 5 times 3, 7 times -2. Then if I move on and do my first row, second column, we'll get the position here. So that'll be 5 times -7, 7 times 5. Second row, first column gives me this one. So we get 2 times 3, 3 times -2. And then finally, second row, second column gives me my last piece, which is 2 times -7, 3 times 5. So if we go ahead and go through this, that'll be 15 minus 14, -35 plus 35, 6 minus 6, and then -14 plus 15. So you do end up with the identity matrix. So this way works well, but now I need to switch the order and see if we get the identity back as well. Just because it worked on one side doesn't mean it's going to work on the other. So I want to go through the same process. So we take first row, first column to get our first row, first column. So 3 times 5, 7 times -7 times 2. Then we do first row, second column to get this position. So that'll give us 3 times 7 plus -7 times 3. Then second row, first column gives us this spot. So we get -2 times 5 plus 5 times 2. And finally, second row, first column gives us this last piece. So if we go through it, that's going to give us 15 minus 14, 21 minus 21, -10 plus 10, and -14 plus 15, which is in fact the identity. So when you did both multiplications, you got the identity back, so we can say they are inverses of each other. So now how, if I just give you a matrix, can we go about finding that identity? So to obtain A inverse for any n by n matrix for which the inverse actually exists, we're going to complete the following. First thing you're going to want to do is you want to make an augmented matrix where you put A on one side, a bar separating it, and then the identity itself. Then we're going to perform row operations on this augmented matrix, just like we did the Gauss-Jordan method, to turn the left-hand side into an identity matrix. The right-hand side is going to be something completely different because you're going to perform the row operations on the right as well. Once you get that matrix A to the identity, the thing you have on the right-hand side is exactly going to be your inverse. So let's go ahead and find the inverse of one of the matrices from the prior example. We already know what this inverse is because we showed this matrix and the other were inverses. So we're going to see we get to that same step. So the first thing I want to do is I want to make this augmented matrix. So I want to put A itself on one side, a bar, and then the identity on the other. So we're forming this augmented matrix. Now I want to use row operations to turn my matrix A into the identity. So we're going to do this just like we solved the system of equations. Gauss-Jordan method did turn that thing into the identity. So your first step is you get a 1 in this position. So you turn this into a 1. So I need to take this entire first row, divide it by 5, and that becomes my new first row. So this will give me 1, 7 over 5, my bar. I've got to do the same thing on this side. So I get 1/5, 0. And then my second row, I leave untouched. After you turn that element to a 1, you turn everything underneath it into zeros. So we turn these into zeros. So I need to go through a matrix operation. I want to take -2 times the first row, add it to the second, and it'll be my new second row. So really, my first row is going to stay completely untouched. And I'm going to go ahead and do this actual operation off to the side. So I want to take -2, row 1, add to it row 2, and that's my new row 2. So if I take -2, row 1, that'll give me -2, -14/5. I've got my bar, -2/5, and 0. I want to add to it row 2. And when we add these, we'll get 0, 1/5, -2/5, and 1. So my new second row becomes exactly what we just found. Okay. Now I need a 1 in this diagonal position. So I go ahead and turn this into a 1. So what I need to do is I need to just get rid of that 5. So I'm going to multiply the entire second row by 5. First row, nothing changes. When we multiply 0 by 5, you get 0. This will become a 1, -2, and then this becomes a 5. And the very last thing I have to do is turn this into a 0. And that'll get the identity on the left-hand side. So I need to make this coefficient match up but be opposite in sign. So I want to take -7/5 times my second row, add it to my first, and that's my new first row. So right now, my second row is staying completely untouched. So I want to take -7/5 row 2, add row 1, and there's my new row 1. So if you multiply the second row by -7/5, you'll get 0, -7/5. That'll become +14/5, and then this will be -7. Then we just go ahead and copy row 1, and we add them together. So that'll give us 1, 0, 3, 7. So those elements go here. So what this tells me now is what I'm left with on the right-hand side is my matrix inverse. So A inverse is exactly the matrix 3, -7, -2, 5, which is what we had there before. So this was the second matrix we verified was the inverse. You have a 3 by 3 matrix that you have to find an inverse of. The same process is going to follow. You perform that Gauss-Jordan method until you get the identity. So it's a little bit more work. Use a calculator to help you out. And again, take those steps you need to be cautious with it. Okay. So now the real reason we went through this whole process of finding a matrix inverse is it's going to help us solve a system of equations. So suppose you have a matrix A, which is n by n, and it's got an inverse. You've got a matrix X, which is n by 1, and it's got a bunch of variables. And B is an n by 1 matrix of numbers. Then, if you have this matrix equation, AX equals B, it's going to have the solution X equals A inverse B. Because if you multiply by A inverse on both sides, this will cancel and give you the identity. But the identity times anything is just itself. So you end up with exactly the solution for our variables to be A inverse B. Okay. So let's utilize again the same matrix we've been dealing with before. Let's solve this system using the inverse of the coefficient matrix. So really, if you notice and you look at these coefficients, we're going to pull those off into our matrix A. So this can be written in matrix form as the coefficients times that variable vector, because if you went through and actually multiplied these, this first row times the first column would be 5 times x plus 7 times y, which is exactly what we have here. If you went through the next one, 2, 3 times xy is 2x plus 3y. So we're able to rewrite that left-hand side in this matrix form. And that needs to equal the matrix for -1. So this is A, x equals B. So I already know this matrix from the prior example. Its inverse is given by this. So the solution to the system will be A inverse times B. So I'm going to take my matrix A and multiply it by B. So it's a 2 by 2, and then it's a 2 by 1. That will go ahead and give you a 2 by 1 vector. So that's going to be what xy is equal to. So we just need to perform this matrix multiplication. I'm going to take my first row, multiply it by first column. So we get 3 times 4 plus 7 times -1. Then we go ahead and take our second row, first column, to give us -2 times 4, 5 times -1. So now we just need to simplify. That's going to be 12 plus 7, -8 minus 5, and I end up with the matrix 19, -3. So this is exactly my matrix X. So X, which is our X and Y variables, are going to equal 19, -3. So the solution to this system is X equals 19, Y equals -3. And if you did want to check, here's our original equation. If you plug in X is 19, Y is -13, it does indeed work. And then same thing if you plug it into the second equation. Okay. Now, realistically, you're not going to need to pick and choose or solve in a specific way when you're going through this system of equations. But that doesn't mean you don't want to throw out these operations. You're going to need to know how to calculate inverses. You're going to need to be able to do matrix multiplication. So you'll still be tested on that material. But if you do prefer one method to solving a system, that's perfectly okay.